Good afternoon. My name is Kelvin and would like to present my work, Paella, which is a low-latency model serving system that features software-defined GPU scheduling. Machine learning serving systems are essential for multiplexing different users and models over limited GPU resources. For example, in NVIDIA's Triton, clients can first register the models into the server, which will then load the models into the GPU. The system will then schedule and run the request on the GPU, potentially sharing one GPU for multiple requests by multiplexing over time or space. Unfortunately, despite last strides towards improving the performance of these systems, today's serving platforms continue to struggle to provide low latency, particularly when the GPU is heavily shared and the models exhibit high dispersion. Now, you might be thinking, why do we need to share GPUs? Today's large language models can reach sizes of hundreds of billions to trillions of parameters. Why do we need to have multiple models share a single GPU? Well, there are a few reasons. For one, for some users and applications, those trillion parameter models may be overkill. If multiple models are able to fit on a single GPU, sharing is essential to save costs. Even when using large language models, there have been significant recent interest in parameter-efficient fine-tuning using techniques like LoRa. These adapters are kept small for both saving GPU resources and for better data efficiency during training. Serving multiple parameter-efficient adapters concurrently requires sharing the GPU. Finally, recent work has shown that even if a model is able to fill a GPU on its own, splitting it over multiple shared GPUs can reduce serving latency under bursty workloads. Unfortunately, existing systems often struggle to share GPUs efficiently and can sometimes even contribute more to end-to-end latency than the computation itself. There are a couple of primary reasons for the inefficiency of today's systems. One major bottleneck is the behavior of modern GPU hardware schedulers, which play an important role in the end-to-end serving performance, but often clash with application-level scheduling needs. One concrete example is the head-of-line blocking that can be introduced by the GPU scheduler. When multiple inference requests are submitted to the GPU concurrently, they will be serialized to a hardware queue. The GPU dequeues and executes the kernels in a strict FIFO order. Unfortunately, this can prevent execution of available kernels and underutilizes resources. I should note that modern GPUs have multiple hardware queues to mitigate this issue, but the hardware queues can still cause head-of-line blocking as number of hardware queues is still fixed. Specifically, if we run even more models concurrently, we face the same problem again. Even worse, having multiple hardware queues creates additional issues with interleaving. Let's run this example to demonstrate the problem. Here, we have two jobs with two sequential kernels each, and a GPU with enough capacity to run two kernels at a time. At t equals 0, the first layers of blue and orange model execute, filling up the GPU. Then at t equals 1, they finish and release the slots. Now, the GPU will continue to round robin between the queues and execute the first layers of gray and purple model. At t equals 2, they finish and the second layers of blue and orange model execute. At t equals 3, the blue and orange model finish. Now, the second layers of gray and purple model execute. At t equals 4, they finish. To summarize, The blue and orange models finish at t equals 3, and the gray and purple models finish at t equals 4, giving an average job completion time of 3.5. Note that a much better execution would have been that finished executing jobs before starting new ones. In this case, the blue and orange models will finish at t equals 2 rather than t equals 3, lowering the average job completion time. Note that this scheduling policy is not achievable using today's GPUs and traditional model dispatch methods. Unfortunately, the rest of the model serving pipeline is typically not much better and includes many other overheads to end-to-end performance. For example, this graph shows for NVIDIA Triton the amount of time spent inside Triton code as a percentage of the actual execution time of the kernel. Note that batching, while it amortizes some of these overheads, actually increases the time to a result that it introduces extra data copy overheads or delay for waiting for a batch of requests. In Paella, we argue that to achieve low end-to-end latency, serving frameworks need tighter integration with their surrounding components and finer-grained control over their scheduling and operation. This includes a co-design between compiler and scheduler to bypass GPU hardware scheduler, and a service architecture for request submission and results retrieval for minimal communication overheads. To use Paella, the clients will first compile the models with our compiler and register them into the dispatcher. Then they can submit requests to the dispatcher, which schedules requests to execute on the GPU and monitors the resource usage and completion. When the request completes, it notifies the client and the client retrieves the output. At the core of Paella is a technique to enable software-defined scheduling of GPUs. The key idea is to only dispatch kernels that can run immediately so that the GPU will not have a queue and so has no chance to make scheduling decisions. Now, we can make our own ones in software without being interfered by the GPU. To achieve that, kernels that we dispatch have to fulfill two requirements. First, the GPU should have enough resources to execute the kernels immediately. This is challenging because this relies on the fine-grained knowledge about resource utilization. Second, the kernels we launch should have no unresolved dependencies. This is also challenging to achieve because we need to control every single kernel launch. To tackle the first challenge, we obtain knowledge about resource utilization by resource tracking. The dispatcher will first obtain resource usage of each kernel, and the kernel will send start and end notifications to the dispatcher when it starts and ends, respectively. Each notification contains a kernel ID so that the dispatcher knows which kernel is starting or ending. Also, it contains a streaming multiprocessor ID which says which GPU core does the kernel runs on. But the kernel won't send notifications by itself, so we need to instrument the kernels with a special compiler to insert codes that send notifications through a channel. The second challenge is that we need to control kernel launch. Originally, CUDA kernel launch is out of our control. When the GPU program runs, it will submit all kernels immediately, and the GPU will decide when to execute them. To obtain full control over kernel launch, Paella inserts coroutine yields before each of them, and unyielding only when the dispatcher decides to run them. By doing that, Paella obtains full control over when to execute the kernel, and the GPU has no chance to make its own decisions. We now have a plan on resource tracking and controlling kernel launch, but both rely on efficient GPU-CPU communication. For resource tracking, we need to receive many notifications from GPU kernels. For controlling kernel launch, we need to anneal as soon as possible after receiving end notifications. So we implemented a shared memory lock-free ring buffer as the communication channel to minimize overheads. With the above components, we define Paella job, which mainly contains a coroutine that launches the kernels. And each CUDA kernel will notify dispatcher about start or end through the ring buffer channel. To submit a Paella job from a client, the client will communicate with the dispatcher using the client library, which internally uses another shared memory channel for minimum overheads. To be specific, the client will run the predict function to submit a job and can run it multiple times to execute jobs concurrently. After that, the client will wait for completion and then read the output. The dispatcher runs an infinite loop. For each iteration, it waits and receives notifications from the GPU to update resource utilization and the wait list. The wait list contains all ready jobs which have no unresolved dependencies. After the updates, it schedules the next kernel from the jobs in the waitlist. Our default scheduler is a combination of shortest remaining processing time, or SRPT, and fairness. SRPT will estimate execution time of each kernel by profiling, sum the remaining execution time of each job, and sort them. SRPT protects short jobs under high dispersions, and so improved average job completion time. The fair mechanism will constrain SRPT-related unfairness by a configurable threshold. Any user that is too unfair will be sorted at the beginning, regardless of SRPT. These scheduling algorithms are possible because scheduling is software-defined, and so we can use high-level knowledge like execution time and user to make scheduling decisions. Also, this allows configurations like the fairness threshold. We evaluated our system on an NVIDIA T4 GPU, and we also tried the larger GPU and the trend host. Experiments run with a mix of 8 vision models of diverse sizes. The requests are generated with an arrival pattern of log normal distributions with 2 different burstiness. We implemented most parts of our system from scratch, but built our compiler based on TVM. We first focused on the system aspect of Paella to factor analyze the sources of the performance gains. We show 2 graphs here. The left is for a smaller model and the right is for a larger one. The x-axis represents the average throughput and the y-axis represents the tail latency. Lower latency and the higher throughput is better. We first compared an ablation of Paella with Triton. The ablation of Paella shares the same code base as Paella, but uses legacy scheduling, meaning that it suffers from head-of-line blocking, interleaving, and other problems we mentioned earlier, just like Triton. We can see that Paella performs significantly better than Triton. Since both systems use the same scheduling, we know that the performance improvements come from the lower system overheads. To further study the system overheads, we use a simpler baseline CUDA, which runs GPU jobs directly without any serving system. Its scheduling algorithm is naturally legacy. Surprisingly, we find that CUDA performs significantly worse than the ablation of Paella, which also uses legacy scheduling. The only difference between the two are the GPU-CPU communication mechanism. While the CUDA synchronization primitives scale poorly with a concurrency, due to some mutex in the CUDA runtime, the shared memory lock-free ring buffer we implemented is a lot more efficient. So Paella has even lower system overheads than using no system. Then we further demonstrate that Paella can achieve even better performance with better scheduling algorithms. Here we show that SRPT scheduling achieves lower average job completion time by favoring smaller jobs. Finally, we demonstrate the configurability of a fully software-defined scheduler. In this graph, we use our default scheduler that combines SRPT and fairness, and we can tune the fairness threshold to decide how much we bias towards SRPT. To summarize, we show that existing machine learning serving stacks are fundamentally limited by the GPU. To solve this problem, we lift scheduling out of the GPU hardware by the co-design of compiler, instrumentation, and an efficient dispatcher. We demonstrated that Paella is a practical system and is flexible enough to support different scheduling algorithms for different trade-offs. Paella is open source on GitHub. Please check it out if you're interested. This is the end of my presentation. I'm happy to answer any questions.
Okay, unfortunately we can't seem to get Kelvin, but luckily the second author, Max Demoulin from DBOS Inc. is here to answer questions you may have about the work. So thanks, Max. Why don't we start on my right?
Okay, thank you. Peter Maucher, KIT Karlsruhe. So the scheduler is usually meant to increase utilization. Do you see any decrease in GPU utilization, and how much reverse engineering did you have to do to guarantee high utilization?
Yeah, good question, thanks. Usually, so I think for the models we're looking at, we had good utilization. Specifically because we answered this problem that if you use the naive scheduler that is baked in the GPU, you can have all those head-of-line blocking and have a lot of SMs that are not going to be used. In terms of reverse engineering, so the real-time community, they did it the hardcore way. They really tried to reverse engineer how the hardware is made. We've been trying to abstract away as much of the parameters you can use for scheduling. So if you look at what the GPU uses under the hood to do block to SM scheduling, they're going to use stuff like registers, number of threads that your blocks are using, the memory bandwidth, etc. We mostly rely on kernel execution time. So that limits a lot the reverse engineering we had to do. And thanks to our instrumentation, we're able to do kind of easy profiling and get a very good approximation of how long these kernels are running. Does it answer the question?
Yes, it does. Thank you.
Hello, this is Zun Yao from SASTech. My question is that I'm curious about your characteristic of the workload. What's the ratio of the kernel execution time to the CPU-GPU communication time? My assumption is that kernel execution is quickly and is fast, and communication is slow. But when your experience is that the communication is slow, the kernel is maybe longer than communication, right?
Yeah, so that's a good question. Essentially, the question is, does our technique works for large kernels that takes, I guess, a lot of time to execute, and don't you have a lot of overheads doing kernel by kernel dispatching when you have these big kernels? So not all models have a uniform distribution of execution time for the kernels. And what we found is that if you have enough concurrent kernels to execute, you will be able to amortize the cost of waiting for some kernel to run, and you can dispatch some others. I think more generally, this technique, this kind of system works very well when you have a lot of potential concurrent models, and you have like also a lot of heterogeneity between kernel execution time. Like the picture you saw with SRPT actually is shortest remaining processing time is fairly representative of that. Like sometimes when you have these models that have a lot of big kernels, they are going to block the shorter kernels. So that's kind of how, for many workloads that you have the situation you can exploit. If you have the right scheduling, you can go over that problem.
Yeah, thank you.
I'm sorry, Demetrius, I don't think we're going to have time. Yeah, maybe take it offline. Awesome. Let's thank Max.